Okay, now we will go through the class 11 physics, chapter 11 thermodynamics. So in winter, when you rub your palms together, we feel warmer. Here work is done is converted and produces the heat. Okay. Similarly, steam is used to do useful work in moving the pistons in the steam engine. So what is heat? Heat is a form of energy. Okay, heat is a form of energy. So conversion of energy from one form to the another, like you can convert a work to heat. What is thermodynamics? Thermodynamics is the branch of physics that deals with the concepts of heat and temperature and the intent conversion of heat and other form of energy. These are all the macroscopic variables. Okay, pressure, volume, temperature. These are macroscopic, high level variable. Okay, in mechanics, our interest is in the motion of the particle or bodies under the action of the forces, torques. But in thermodynamics, thermodynamics is not concerned with the motion of the system as a whole. Okay, thermodynamics is not concerned with the motion of the system as a whole. So what is equilibrium? Okay, and the equilibrium fixed values of the pressure, volume, temperature, mass and the composition that do not change with the time. Okay, then that is the state of equilibrium. In this equilibrium state, there is no change in pressure, volume, temperature, mass and okay. This is a adiabatic valve, so it cannot exchange heat with the surroundings. Okay, so there will not be any change in the variables here. This is diabatic. It can exchange the properties with the surroundings, heat with the surroundings. Systems A and B, two gases separated by an adiabatic wall. Okay, this is adiabatic wall and an insulating wall. Okay, adiabatic is insulating wall that does not allow the flow of heat. Okay, with the surroundings. B, the same A and B separated by a diabatic wall, that is a conducting wall that allows heat to flow from one another. That is, in this case, thermal equilibrium is attained. Okay, it can exchange heat with the surrounding, but not here. This is entropy is a disorder. Okay, entropy is measure of disorderness in the system. Enthalpy is the measure of total heat content of the system. Okay, enthalpy and entropy differentiation. No, entropy is the disorderness, enthalpy is the total heat content. Adiabatic wall. Okay, so in adiabatic it cannot exchange heat with the surrounding. So it is found that any possible value of pressure volume will be in equilibrium with any possible values of the pressure and volume because it cannot exchange. So there won't be any change in the pressure and volume. Okay. Diathermic wall, here it can exchange the heat with the surroundings. There is no when it assigned equilibrium, there is no more energy flow from one to the another. When we then say that system A is thermal equilibrium with the B. So when it the surrounding temperature is equal to the inside temperature, then it is assigned the equilibrium, thermal equilibrium. What is zeroth law of thermodynamics? two systems in thermal equilibrium with the third system separately or in thermal equilibrium with each other. This is the zeroth law. See, if A and C are in thermal equilibrium and B and C are in equilibrium, that means that A and B are in the equilibrium. Okay, this is a conducting wall. A and C connected, B and C connected. These two, that means A and B are in equilibrium indirectly. That is what the zeroth law. So here A and B are connected. Okay, but this is not connected. Okay, the adiabatic wall between A and B is replaced by a conducting wall. This is a conducting wall where C is insulated from A and B by an adiabatic wall. Both the variables need not change. It depends on the constraint. For instance, if the gases are in containers of fixed volume, only the pressure of the gas would change to achieve thermal equilibrium. Heat, internal energy and work. Temperature is the marker of the hotness of the body. Heat flows from the higher temperature to the one in the lower temperature. Internal energy, that is U, symbol U, is simply sum of the kinetic energy and potential energy of the molecules. Okay. Internal energy symbol. The macroscopic variables of the system. Internal energy depends only on the state of the system. Okay, that is initial and final state. It is independent of the path. It is not dependent on the path. So internal energy is a state variable. A gas in motion is not only in the translation motion, it also includes rotational and vibrational motion. Okay, gas in motion, in addition to translation, it also has rotational and vibrational motion. Internal energy of a gas is sum of the kinetic and potential energy of the molecules. When the box is addressed, box is addressed, kinetic energy due to the various types of the motion, translational, rotational, vibrational, is included in U. Okay, in the internal energy. If the same box is moving as a whole with some velocity, the kinetic energy of the box is not to be included in it. Okay, if it is moving as a whole, then kinetic energy of the box is not included to it. Okay, how this heat and work is converted to energy. Heat and work are two distinct modes of energy transfer, okay, to the system that results in the change of the internal energy. A heat energy transfer due to the temperature difference between the system and the surroundings. Okay, heat energy transfer due to the temperature difference between the system and the surrounding. Okay, that is between the temperature difference between system and surrounding. B, work energy is transferred is brought about by moving the piston, by raising or lowering some weight. Okay, is connected to it that do not involve such a temperature difference. Okay, so both and heat can transfer the energy. You can change the internal energy using this work, or when there is a temperature difference between the system and the surrounding. When you do work on the system, then it changes internal energy. Okay, a statement like a gas in a given state has a certain amount of heat is meaningless. Heat is a flow of energy, is a meaningless. But here a gas in a given state has a certain amount of internal energy, that is a meaningful. Okay. What are the state and path variables? Okay, the heat and work in thermodynamics are not state variable, depends on the path. Okay, but internal energy which is depends which is a state variables, it is not, it is independent of the path. First law of thermodynamics connect the heat supplied to the system, okay, with the work done by the system. Del change in internal energy of the system. Okay, heat supplied to the system, change in internal energy, work here, work done by the system on the surroundings. Okay, this is nothing but the principle of conservation of energy. Okay, this first law of thermodynamics. So you can rewrite the equation. Change in internal energy is heat supplied minus work done on the system. Okay, delta U depends on the initial and final states, so this is not on the path because this is a state variable. Okay, but here delta K in general depends on the path taken. Okay, internal change in internal energy 0 for a isothermal process. Isothermal, that is a constant temperature. Specific heat capacity. Okay, this is change in the heat divided by the change in temperature. Okay, this is not meaningful. You have to represent per gram. Okay, to define a constant characteristic of this substance independent of its amount. Okay, it depends on the amount, so independent of the you have to define per gram or per kilogram. Okay, this is the specific heat capacity. So this depends on the nature of the substance and its temperature. So when the moles are given, then you have to use the molar specific heat capacity. This is the number of moles. Based on the given data, whether moles are given or mass is given, then you have to use the specific heat capacity or molar specific heat capacity. These are the specific heat capacity of the some substance. This is the water specific heat capacity of the water. What is 1 calorie? 1 calorie was earlier defined as the amount of heat required to raise the temperature of 1 gram of water by 1 degree C. But later this is specific. Okay, that is the definition. Specific heat capacity of water is 4186 joules per kilogram per Kelvin. This is per gram per Kelvin. Okay, this is for the kilogram and this is for the gram. So for the gases, we define specific heat capacity at constant volume and specific heat capacity at constant pressure. These two parameter we define for the gases, and this is the relation. Okay, constant pressure and constant volume minus constant volume equal to the R, universal gas constant. Okay. This is the ideal gas equation. For an ideal gas, BV equal to mu R, mu is the number of moles. So here isotherm means at the constant temperature. Okay. The pressure volume curve at a fixed temperature is called isotherms. Pressure volume curve at a fixed temperature is called isotherms. What is intensive and extensive variables? Extensive variables indicate the size of the system. Okay. Intensive variables such as pressure and temperature, they do not depend on the amount of the substance. Okay, intensive variable is independent of the amount of the substance. So to decide which variable is extensive and which is intensive, think of a relevant system in equilibrium and imagine that is divided into two equal parts. When you divide, the variables remain unchanged and each parts are intensive variable like temperature, so it does not depends on the quantity amount. Okay, the variables whose values get upped in each part is extensive. Okay, example mass. It is easily seen from the internal energy, U, volume, V are the extensive variable. Okay, these does not depend on the the variable that remain unchanged. Okay, the internal energy, volume and the mass are extensive variables, so this depends on the amount. Pressure, temperature are the density or the intensity variable that is not depend on the amount of the substance. Okay, extensive and intensive, but when we multiply a intensive variable like pressure with an extensive variable like delta V, the quantity, the result will be extensive. Okay, the product of the intensive variable like P and an extensive quantity W is extensive. Okay, this is important. In a non-equilibrium state, we cannot apply this PVT rules. Okay, ideal gas equation in the non-equilibrium states. Q is not a state variable. However, delta Q is proportional to the total mass of the system and hence it is extensive. Okay, Q is not a state variable, delta Q is extensive. So what is quasi-state process? That change occurs infinitely small, very slow process. Is a very slow process, quasi-state process. What is isothermal process? Process in which temperature of the system is kept fixed throughout the throughout is called isothermal. Isobaric pressure fixed, isosteric volume fixed. No heat flows between the system and that is a adiabatic process. Okay, these are these things: isothermal, temperature constant, isobaric, pressure constant, isothermic, volume constant, adiabatic, no heat flow between the system and the surrounding, delta Q equal to 0. Isothermal process, PV equal to constant. What does that mean is when you increase the pressure, then volume automatically decreases. That means PV constant. When you increase the volume, pressure decreases. So that is the constant. Boyle's law. Substitute for P from PV equal to nRT, then you will get this equation. No change in the internal energy when ideal gas for the isothermal, that is a constant temperature. Adiabatic process, delta Q is 0. Adiabatic process, this is specific heat capacity ratio at constant pressure by constant volume is denoted by the gamma. So I took this value is 1.4 from the net. Okay, for some problems we are using this value. Cp by Cv for the ideal gas is 1.4. This power gamma is here. This is isothermal, this is also isothermal, this is adiabatic process. PV curve for the isothermal adiabatic process of the ideal gas. In a adiabatic process, if work done on the gas, then work will be negative. Adiabatic process, work done on the gas, that means W will be negative. So when a cyclic process, that means delta U is 0 because it is a state variable. It depends on the initial and final states. When both states are same, then delta U is 0. Second law of thermodynamics. Okay, this is the second law. No process is possible whose sole result is the absorption of heat from the reservoir and the complete conversion of heat into work. Okay, that is 100% efficiency is not possible. That is the meaning of this. This is a separate statement. Okay, no process is possible whose sole result is the transfer of heat from the colder object to the hotter object. Spontaneous process of the nature are irreversible. What are reversible and irreversible process? Why it is irreversible? Process why become irreversible? Irreversibility arises mainly from two causes. One, many processes like the free expansion or the explosive chemical reaction take the system to a non-equilibrium state. Okay. Friction, viscosity and other dissipative effect, that is taking system into the non-equilibrium state. This is the Carnot engine. So in this Carnot engine, so we have a system at particular pressure, volume and temperature, then it expands isothermally. Okay, this is isothermal, this is also isothermal, this is adiabatic, this is adiabatic. Okay, from this volume to this volume and this at the same temperature, isothermal. Okay, now here adiabatic, that means delta Q equal to 0. That means delta Q is 0 when pressure volume changes, that means temperature will change. Okay, inside the temperature will change because it cannot exchange heat with the surrounding area. So inside temperature will change T1 to T2. Okay, similarly this is also isothermal compression here, this is isothermal expansion. Okay, these steps are mentioned here. That is a reversible engine. These steps is step 1, isothermal expansion of the gas. Okay, here heat is absorbed. In steps 2, adiabatic expansion, work done by the gas. Okay, because it delta Q is 0, there is a temperature change or work done by the gas. Step 3, isothermal compression, heat is released. Okay, similarly this. Okay, these steps you can go through it. And finally this is the equation for the Carnot engine, reversible engine. Okay, so this experiment they are doing A and R. Okay, you can go through it. And this is the relation between Q and T, where Q and Q2 respectively are the heat absorbed and release. Heat absorbed and release, and this is the temperature change, that is Carnot cycle. Okay, summary again, this is zeroth law. Heat and work are the two modes of energy transfer. The first law of thermodynamics. So is specific heat capacity, molar specific heat capacity, this relation. What is 1 calorie? Okay, this amount of heat required to raise the temperature 1 gram water from 14 to, okay. This is the relation. Okay, what are state variable and what are path variables? Quasi-state process, infinitely slow process. Isothermal expansion, adiabatic process. Okay, second law implies that no heat engine can have the efficiency equal to 1. That is 100%. No, that is not possible. That is what second law. This is the Carnot cycle, that formula. This is the important thing. Q is greater than 0. That is Q, total heat greater than 0, heat is added to the system. Q is less than 0, heat is removed from the system. W greater than 0, work is done by the system. W less than 0, work done on the system. Okay, these are some quantities and dimensions. Okay, we will go through the exercise. A geyser heats water flowing at the rate of 3 liters per minute from 27 to 77 degree. If the heater operates on the geyser operates on a gas burner, what is the rate of consumption of the fuel if the heat of combustion? Okay, this is the fuel combustion. Okay, so we have to find the total energy to require to raise the temperature of 3 liter from this is delta T is 50. This is the mass of water, and we know the specific heat capacity of water. Okay, if this equation, specific heat capacity of into mass, ms into delta T, that is the total heat required. So specific heat capacity of water here is 4.186 joules per gram. I am using per gram per Kelvin. Okay, so now mass is in terms of grams. Here I have taken in terms of grams. So here also I am taking in terms of grams. So then multiplying the specific heat capacity, then delta T is 50, because 77 minus 2750, this much total heat required, but the heat of combustion that it can supply only this much per gram. So the rate of combustion will be this divided by this. So this many grams per minute, we will burn this much grams per minute. Okay, so here is the formula. Okay, delta Q equal to delta T into ms. Okay, what is the amount of heat must be supplied to the 2 into 10 power minus 2 kg of nitrogen, okay, at room temperature nitrogen is a gas, to raise its temperature by 45 degree at constant pressure. They are asking at molecular mass. Okay, see, from the given data we should know what to use. So here we are going to use the molar specific heat capacity. Okay, they given molar mass of nitrogen, then we will find from this mass using molar mass how many moles. Okay, then they are given at the constant pressure. Okay, we are going to use this formula using the moles. Okay, here this is molar number of moles, molar specific heat capacity. Okay, me equal to moles. This is the weight of this nitrogen. Then divided by the molar mass will give the number of moles. Okay, this means 0.714 moles. They are given molar specific heat capacity at constant pressure. Okay, this Cp equal to 7 by 2 R, that is a universal gas constant. So this is the relation for that ideal gas. Okay, so you can see from the net this relation. So now the delta Q equal to mu 0.714 and then Cp constant pressure. So 7 by 2 into gas constant, then delta T is 45. Okay, this many, so this many joules heat. Okay, now this is nitrogen is a gas at room temperature. Amount of heat. Okay, okay, explain why two bodies at different temperatures is brought in thermal contact do not necessarily settle at the mean temperature. Okay, because these two can have different heat capacities and different masses also possible, different masses also possible, and they can have the different heat capacities also. Because of that reason they may not settle. Two bodies thermal contact not necessarily settle at the mean temperature. The coolant in the chemical or nuclear plant to prevent the different parts of the plant from getting too hot should have the high specific heat capacity. Okay, the specific heat capacity means that means the rate at which it can absorb heat. More specific heat capacity means it can absorb heat very fast, so it will avoid the rise in temperature. Okay, means higher rate of absorption of, so that T variation will be very less. Okay, that is why it should have the high specific heat capacity, so the absorption of heat rate will be more for that. Air pressure on the car tire increases during the driving. Air pressure on the car tire increases during, so ideal gas equation BV equal to NRT. Okay, so when volume remains constant during driving, temperature increases. Okay, during driving the tire temperature increases but volume remains constant, so this has to increase, so pressure has to increase. Okay, PV equal to constant, when temperature increases volume remains constant, pressure has to increase. The climate of the harbor town is nearly temperate. Temperate means it's like a moderate, it will not change that much. than that of the town in the desert. Okay, so here again the specific heat capacity of the sand in the desert is very small. That means it can very large. But for the water specific heat capacity is 4186 joules per kilogram here, you see. So that is why it is moderate. In the harbor town there will be more water on the air than on the desert town. So the specific heat capacity is less for the sand, so it can vary drastically. A cylinder with movable piston contains 3 moles of hydrogen at the standard temperature and pressure. The walls of the cylinder are made heat insulated, that is adiabatic. It cannot exchange heat with the surroundings. And the piston is insulated by a pair of sand on it. And what factor does the pressure of the gas will increase if the gas is compared to the half of the initial volume? That is a adiabatic process. Page 10. For the adiabatic process, this is PV, then gamma is constant. This gamma is nothing but the molar specific heat capacity constant percent by calling this value is 1.4. Okay, these two equations we are going to use. P initial volume initial equal to P final volume final per power this gamma. The adiabatic process PV power that gamma equal to constant. So this value is 1.4 from the net. You can see this ratio, or from some other chapter also may be there in the your syllabus. Constant pressure, constant volume, gamma. So initial volume initial P initial volume initial equal to P final volume final. So the final volume is half of the initial volume. Okay, VI by 2. So VI by 2, then after that you will get P final by P initial equal to 2 power 1 power. So this is the ratio, the final pressure to the initial pressure. Okay, by what factor? Okay, that is the factor. In changing the state of a gas adiabatically from the equilibrium state A to the another equilibrium B, the amount of work equal to the 22.3 joules done on the system. Okay, on the system, work done on the system, page 10. See, work done on the system, it will be negative. W is less than 0, then negative. Okay, if the gas is taken from state in the process in which net heat absorbed by the system is 9. Okay, how much is the work done? So this is first law of thermodynamics. So our adiabatic process delta Q equal to 0. This work done is negative. Okay, so delta U, this is 0. That means delta U is 22.3 joules. Because this is negative, I showed you work done on the system. So now work done equal to delta from this equation, delta W equal to delta Q minus delta W. This we are converting to joules. Then after that you will get this much work done. Okay, I already showed you this why negative, we are using the negative sign here. Two cylinder A and B equal capacity are connected to each other by a stop cock. That means it's like a valve. A contains the gas at standard pressure, B is completely evacuated, the entire system is thermally insulated. Is suddenly opened. Answer. What is the final pressure of A and B? Okay. PV equal to nRT. Okay. For volume increases, that means pressure decreases. Pressure decreases. Volume increases by 2 times. So pressure will decrease by half. Then only it will be a constant. What is the change in the internal energy of the gas? Gas expands automatically. There is no work done. Okay, so no change in the internal energy. Okay, thermally insulated, no change in the internal energy. What is the change in temperature of the? No change in temperature because no work done. Do the intermediate states of the system before settling to the final equilibrium? Oh no, it won't obey this intermediate phase. They are not in equilibrium. Okay, they are not in equilibrium, so it won't obey those laws. The non-equilibrium phases do not have the well-defined pressure and temperature. Okay, they don't obey that in the intermediate states. The electric heater supplies a heat at the rate of, this is the total heat supplied. If the system performs work at a rate of money, at what rate this internal energy is increasing? The given delta Q 100, delta U they are asking internal energy change, and delta W again delta U. Okay, this much. Thermodynamic system is taken from the original state to the intermediate state by the linear process is shown. Its volume is then reduced and the original value from it here. Okay, calculate the work done. Work done is nothing but the area under the curve. Okay, this is a triangle. Area of the triangle is half BH, 1 by 2 into this is 2 to 5 3. Okay, half B is 3, H is 300. Okay, this much Newton meter. Because of this Newton per meter square, and this unit, after this unit you will get Newton meter. Okay.